Hi there, it's Tim G5TM back for another video. This is the second video in my series looking at HF mobile efficiency. And what we're focusing on today is the role played by loading coils, whether they're base loaded or center loaded. Now, the last video we looked at the importance of antenna length, the sheer just physical length of the antenna, and also looking at top loading through the use of capacitance hats to try and make the antenna a little bit electrically longer. But of course, most of us who use HF mobile probably use an antenna that has a loading coil, either at the base, which the majority probably will have, but of course there are also center loaded antennas as well. So the key question today then really for us is what do loading coils do on HF mobile antennas? Well, what they certainly do, they insert what's called an inductive reactance to help cancel out a capacitive reactance, and it cancels reactance, leaving only resistive parts remaining. Now what that means basically is it cancels out any reactance and produces a good match for your radio, whether it's a base loaded or a center loaded antenna. Now the thing is, lots of people think that loading coils have other sort of functions, but they don't, because what some people think they do is actually replace the missing fraction of a wavelength. For example, you've got folklore where people say that, well, I've got a half wave antenna, maybe not a mobile antenna, but I've got a half wave vertical, and I'll wind exactly another eighth of a wave, and what I'll then do is turn that antenna into a 5/8. Well, it doesn't quite work like that. By wind an eighth of a wave, I mean wind a coil with exactly 1/8 of a wavelength of wire going around it. Well, that doesn't happen. So one thing that loading coils don't do, they don't replace any missing fraction of a wavelength. So for example, if you've got a 3 meter long whip on your car, which is quite long, a loading coil would not magically turn that into exactly like a quarter wave for 14 megahertz for 20 meters. It doesn't turn it into a 5 meter long whip. At the end of the day, it's still a 3 meter long antenna. But what it does, as it says on the right, it cancels reactance, leaving only resistive parts remaining. So the important aspect here is that coil Q matters. And by Q, we're looking at the Q factor. And we're looking here in terms of having as high a coil Q as possible. And by necessity, having a higher coil Q depends on certain things in terms of how the coil is actually constructed, and also will give you a certain result in terms of bandwidth as well. So let's have a look. Now the ARRL are very clear about their importance of loading coil Q. They stress that loading coil resistance makes up basically one of the biggest losses that consumes power that would otherwise be radiated by the antenna. So therefore, any heat loss in the coil needs to be minimized by using the highest possible loading coil Q. Now the thing is though, when you've got, especially operating on the lower bands, 40 meters and below, then the big difficulties you have is that loading coils, their difficulties increase as you go lower. The required resonating inductance gets larger, and that because of that, the radiation resistance decreases at lower frequencies. So the more you load your antenna, you have to load your antenna with that coil to bring that 2 or 3 meter long whip into resonance and to be able to be used and have a decent match, say on 40 meters or even 80 meters. The bigger the coil inductance has to be, and therefore the more that affects radiation resistance and therefore the efficiency of the antenna. It's just how it is. So most of the power, therefore, is dissipated. It's wasted in coil resistance and in other losses as well. It's just one of the facts of life of operating down on 40 and below with a loaded whip antenna, any loaded vertical, actually, for that matter, with a loading coil. So loading coil design and Q. It says there basically that the design of the loading coil goes a long way to determining the Q. And we want as high a Q as possible. So when we have, for example, large diameter coils, what that means is we've got increased capacitance and more resistive wire losses. So the coil can act more like a lossy capacitor, not a coil. The size of the wire on the coil is important, as we'll see. The number of turns of wire on the coil per inch of the coil length is important. The actual coil support material, in other words, what the coil is wound on, is important and supported by. And anything conductive nearby, like a capacitor hat or any other metal, immediately above or below a coil will also reduce its Q and reduce the efficiency of the antenna. K0BG at the bottom there, who's a bit of a guru when it comes to mobile antenna efficiency. He clearly states that the reason, this is his quote by the way, the reason most antenna manufacturers don't publish their Q ratings is simply because they are really low in the 50 to 60 range. So yes, that is probably the case. When you look at most loaded antennas out there, they have quite skimpy coils, and we can probably assume that their coil Q is probably quite low. You get what you pay for. And that goes for base loaded and indeed for center loaded antennas as well. Okay, so when we're looking at creating a high Q in our loading coil, we should avoid thin wire, use as large as possible conductor, thick wire as possible. We need to create air wound construction, large spacing between the turns, the best insulation material we can use for the former we wound it on. The diameter needs to be, or should not be, less than half the length of the coil, which can be very difficult, especially down on 40 and especially 80 meters and below. And we need a minimum amount of metal in the field of the coil as well. Now this guy, WA5VJB, who featured on the first video, he found that the wire gauge used to produce loading coils affected both the gain and the bandwidth. Now in this case he's using copper wire and comparing it with a full-size quarter wave antenna as the reference antenna. And what he found basically, that for shortened loaded vertical, like a HF whip for example, when you're creating a coil, you can achieve 2 out of the 3 things. You're either looking at the size of the antenna, the gain, or the bandwidth. You can't really get all 3. And if we look at the table that he produced, on the left there you can see that the gauge of the coil wire, as the coil gets thinner as we go down from 14 down to 26 gauge, the gain we get in comparison to the quarter wave reduces from being within 10 dB to now being within 14 dB. But of course the thing we gain by having a less efficient antenna, a lower Q coil, is that we have greater bandwidth. So that ties in with the belief that higher Q coils tend to be narrower in bandwidth and greater in efficiency, like the one at the top of that table, around with 14 gauge. Notice if we've got 32 kilohertz there, and at the bottom we've got an antenna which has a bandwidth, by bandwidth I mean 2 to 1 SWR bandwidth of 82 kilohertz. And that's a 5-foot base loaded mobile vertical antenna relative to a quarter wave. In this case, I believe, on 40 meters. So as it says on the right there, if you're looking at a shortened loaded vertical, you're choosing 2 out of size, gain, and bandwidth. Gain and bandwidth in particular are very, very difficult, if not impossible, with a shortened antenna to have both of those things. So the question is then, what's better? Is it center loading or base loading an antenna? Now the popular belief is that center loading is far better. So let's see if that's the case, shall we? So we're obviously, in the last video we looked at the importance of increasing radiation resistance. We've got 2 options. We top load like we looked at last time. And also the other option we've got, which we'll look at now, is center loading. So we're placing a loading coil further up the whip away from the base. And that should improve the current distribution of the antenna. And we can see here, look, from the ARRL, what we've got here is an antenna. I think this is an 8 foot long antenna. Actually, it's actually 3.2 meters long, so it's a bit about 10 foot long, something like that, on 7 megahertz. On the left, you've got the base loaded version. Look, you can see that's the classic current distribution from the bottom, from the base, and obviously it becomes the very little current towards the top of the antenna. On the right hand side, we've got a center loaded. Now look at the difference there. We've got more greater current distribution around and below the coil. It fattens out the current distribution. So we've got increased uniform current, and that will in particular increase our radiation resistance. So if we look at this then, on this table, at the top you've got base loading at the center, and at the bottom you've got center loading. If I just get your mouse here, you can see where the blue arrow is going to. So this is on 7.2 megahertz. Okay, our radiation resistance is 1.3 ohms. And that gives us an efficiency of around just under 4%. So 4 out of every 100 watts is being radiated by this antenna really. Now, if we switch to center loaded at the bottom, we've now changed that 1.3 to 3 ohms. We've got just over double the radiation resistance. And that by itself, and that's the important thing here by the way, is by itself gives us an efficiency of 8.1. So we're actually over doubling our efficiency, doubling our power, which means that we're about 3.3 dB better off at the bottom, look. So yeah, happy days. So if we center load a vertical like this, we're going to be doubling our power, right? And yeah, I mean, again, if we look at more information, we can see here, look, that the 2 arrows, you can see that, for example, this arrow here, this line here, sorry, it says the A5 arrow is an 8-foot whip at just over 7.2 megahertz, okay? And if we center load it, look, we can see our radiation resistance, okay, is just over 3 ohms. And the base loaded, it's about 1.5 ohms, actually 3.2 and 1.6. And that's uniform for the other lens as well. So, yeah, fine. So if we center load an antenna, it's bound to be at least much better, in fact, giving us an extra 3 dB. Happy days. And yeah, I mean, look at the pros are current distribution on the whip is improved, which increases the radiation resistance. But as with everything, there are cons. And there is something we haven't factored into this yet with center loading. Now with base loading, at the top of that first con here on the left-hand side, look, we just need quite a low value of inductance, okay, down at the base. But as we move the coil higher up the antenna, we require a larger coil. That's because the capacitance of the shorter antenna section above the coil to the car body is now lower. We've got higher capacitive reactance. So we need greater inductance in that center loading coil to tune the antenna to resonance. So what this all means then is that the coil size and the losses increase as we especially go onto lower frequencies. So some of that initial positivity we've just seen here from having a center loaded antenna is actually literally wasted a little bit now, because we need to have a fatter coil because it's higher up on that whip, and therefore that creates that bit more loss. And that therefore takes the edge of it a little bit. So let's look at our 8-foot mobile whip again, same one we looked at just now. Now look at the red arrows this time. Now the red arrows, we're looking at comparing, for example, on this one here, when it's pointing to the number 18, that's a fairly low Q, fairly inefficient coil really, okay? Now, at base loading, you've got a coil resistance of 18 ohms. But when we center load it, it doubles to 36 ohms. Similarly, when we base load it, okay, when we base load it with a higher Q of 300, so that's a better efficient coil. Yeah, our coil resistance is 3, but it still doubles even with a very high Q coil or a fairly high Q coil when we center load it. In other words, when we effectively center load the antenna, we are, certainly for 40 meters, and for other bands it's a similar story, we are doubling the coil resistance. And what this means is, if you look at the middle paragraph here, look, that 8-foot center loaded mobile antenna on 40 meters hasn't got an 8% efficiency, it's now down to about 5.5. All right? That means, therefore, we haven't got a 3.3 dB improvement in our whip from being center loaded compared to base loaded. It's actually about 1.7 dB. So, yeah, okay, it's still an improvement, isn't it? But not quite as good as we thought. 1.5 dB, yeah, okay, it's nice to have that increase, but it's not that brilliant. It's not that much of an improvement. You know, you probably wouldn't hear much of a difference on 1.5 dB on the air, to be perfectly honest with you, would you? I don't think so anyway. Now, the other question is then, okay, why don't we go the whole hog and top load the antenna with a coil? We've looked at how we could use capacity hats before, so why don't we just top load the thing with a loading coil? Well, there's a catch there as well, unfortunately. Now, as this diagram shows, look, I'll just show you one of these lines. Now this line here, line A, the curve up here, look, all right? We have very low ground loss here, which is good. We'll look at ground loss again, right? But with this curve A, this is a very high Q, very efficient coil. all right, and it's center loaded. Maybe it's don't forget, it's an 8-foot long whip, about 2.5 meters long. So if you look along the bottom here, look, this is the loading coil location on that 8-foot coil. So 0 means it's base loaded. And as you go along the bottom where my arrow is pointing to, that's 4 foot. That's center loaded. And if you go up, you can see that's where we get our highest bit of radiation resistance here. It's right at the top of the curve. But if we try to load this coil further along, as further up, look, from the bottom. So if we go, say, to 6 foot up, then we're beginning to lose radiation resistance again. And in fact, if we went to the very top, now that might be mechanically a bit difficult, but if we did go to the top, we would actually be worse than if we'd base loaded it. Now, this one we're looking at here, A, is where we have a very high Q coil and very low ground loss. All right. Now, let's look at an example then of a much lower Q coil with much higher ground loss. So we could look at F, the bottom one here. Now, it's not quite a sharper curve, but it's still a very similar story, look. Look at this one, the bottom one here. Again, if we go to 4 foot above the coil, halfway up the antenna, that's kind of where the peak is. Oh, it's slightly higher, a bit higher up, but it's kind of where the peak is. But look again, if we try to top load it, we're fractionally worse off than we would be, I think, than if we'd base loaded it. So there we are. So no such thing as a free lunch anywhere with this hobby, is there? Center loading, is fractionally better than having the antenna base loaded, for example. But to be honest with you, the common theme is that once you put that coil much higher than halfway up the antenna, the efficiency and the radiation efficiency starts to really drop, okay? And that is a big theme when it comes to center loading. You can't really go much higher, or loading a short vertical, you can't go very much higher really than halfway up the antenna before you see things begin to reverse back again. So there we go. Now if we look back at this again, look, the reason why this happens is because there is a rapid increase in loading coil reactance required above the antenna center. All right. And this rapid increase in coil size required for resonance means you get coil loss resistance. So a bit like how we saw when we moved from the base to the center, we needed a larger amount of inductance, therefore a beefier coil really, certainly a higher Q coil to be able to ensure that we have an improvement in radiation efficiency, because we knew we'd have higher capacitance. As we go above that towards the top, then it's pretty difficult really, in fact nearly impossible, if you use a loading coil to be able to improve the efficiency much more than higher up than center halfway up the antenna. All right, and that's the key thing. So then, if we're looking at some of the realities of center loading very quickly to finish, higher coil Q produces higher radiation efficiencies. Yeah, I think we knew that. Longer antennas, like we saw last time, produce higher radiation efficiencies. Lower ground loss resistances produce higher radiation efficiencies. We'll cover ground loss next time. Higher ground loss resistances force the loading coil above the antenna to reach a crest in the radiation efficiency curve. So again, higher ground loss is an important thing. We'll look at that again. But the important thing at the bottom one here is higher coil Q sharpens the radiation efficiency curves, resulting in the coil position being more critical. And what this basically means is, therefore, if you're going to load it anywhere away from the base, don't go anywhere higher than the center of the antenna. Okay, so there we go, a quick look at it then. Now what we'll do next time, I'm going to look at ground loss next time. We'll go back to center loading versus base loading one more time. And what we'll do next time is look at an example of a range of antennas which are out on the market at the moment, a specific make, which have both base and center loaded. And we'll look at the situation, or the question I should say, what's more important? Is it the length of the antenna, or is it where the antenna is loaded? And that's going to be a critical thing to look at. Anyway, hope you enjoyed that. A bit of a technical thing, but I quite enjoy doing the research as well. And it's knocked away a few misconceptions I might have had about just how much better center loading is compared to base loading. Anyway, if you fancied seeing any more videos, I'll put one up there somewhere, up around there. And if you want to see, if you want to click and subscribe and join the party and join the channel, that'd be wonderful. Then you can do so over there. 7-3, thanks for watching, and we'll catch you again. Bye-bye.